The optional method of calculating feeder and service loads does not apply to residences with large square footage that are served by a 208/120 volts, 3-phase, 4-wire service. The optional method is only applicable to single-phase services. For residences with large square footage that are served by a 3-phase service, you will need to use the general method of calculating feeder and service loads. This method is outlined in Article 220 of the National Electrical Code. The general method for calculating feeder and service loads involves the following steps. Firstly, determine the total connected load of all of the appliances and equipment in a residence. Secondly, multiply the total connected load by the applicable demand factors from Table 220.82 of the NEC. Thirdly, add the results of Step 2 to determine the total demand load. And fourthly, divide the total demand load by the voltage of the service to determine the required amperage. Once you have determined the required amperage, you can select the appropriate feeder and service conductors. Let's say that you are designing a residence with a total connected load of 100 kilowatts. The residence will be served by a 208/120 volts, 3-phase, 4-wire service. According to Table 220.82 of the NEC, the demand factor for a residence is 0.35. The total demand load is 100 kilowatts times 0.35 equals 35 kilowatts. The required amperage is 35 kilowatts divided by 208 volts equals 168 amps. You would need to select feeder and service conductors that are rated for at least 168 amps. To summarize, the optional method of calculating feeder and service loads does not apply to residences with large square footage that are served by a 3-phase service. For these residences, you will need to use the general method of calculating feeder and service loads. Let's delve deeper into each of these steps to provide a more comprehensive understanding. When determining the total connected load of all appliances and equipment, it is crucial to consider every electrical device within the residence, from lighting fixtures and small appliances to large equipment such as air conditioning units, electric ranges, water heaters, and any other significant electrical loads. Each of these items contributes to the overall demand placed on the electrical system. The nameplate rating of each device should be used to determine its power consumption in watts or kilowatts. These ratings are usually found on a sticker or plate fixed to the appliance or equipment. For lighting, the wattage of each bulb or fixture should be added up for each circuit. For appliances, the nameplate rating provides the maximum power draw. Remember to account for all permanently installed equipment as well as frequently used portable appliances. It's also important to consider any future additions or upgrades that might increase the connected load. After determining the total connected load, the next step involves applying demand factors from Table 220.82 of the NEC. Demand factors recognize that not all electrical devices will be operating simultaneously at their maximum rated power. They allow for a more realistic assessment of the actual load that the electrical system will need to support. Table 220.82 provides demand factors for various types of dwelling units and different portions of the connected load. For example, it may specify a lower demand factor for the portion of the load exceeding a certain kilowatt threshold. Understanding how to correctly apply these demand factors is crucial for an accurate load calculation. The demand factors take into account the diversity of usage patterns within a residence. Some appliances are used infrequently, while others are used regularly but not always at full capacity. By applying these factors, the calculated load is reduced, resulting in a more efficient and cost-effective electrical system design. Be sure to carefully read the notes accompanying Table 220.82 to understand any limitations or specific conditions that may apply. The third step is to add the results obtained after applying the demand factors to determine the total demand load. This sum represents the maximum amount of power that the electrical system is likely to be required to deliver at any given time. It is the critical value used for selecting the appropriate size of the service entrance conductors, overcurrent protection devices, and other electrical equipment. The total demand load is expressed in kilowatts or volt amperes. This value is directly related to the amount of current that will flow through the electrical system. It is imperative to accurately determine the total demand load to ensure that the electrical system is capable of handling the expected power requirements of the residents. An undersized system can lead to overloaded circuits, nuisance tripping of breakers, and potentially dangerous overheating of conductors. Conversely, an oversized system is unnecessarily expensive and inefficient. The final step involves dividing the total demand load by the voltage of the service to determine the required amperage. This calculation converts the power demand from kilowatts to amps, which is the unit used to measure the flow of electrical current. The voltage used in this calculation is the line-to-line voltage of the three-phase service, which in this case is 208 volts. The resulting amperage value represents the minimum current carrying capacity that the service entrance conductors must have. It is important to consider the voltage drop when selecting the size of the conductors. Voltage drop occurs as current flows through a conductor, and it can reduce the voltage available at the load. The NEC specifies maximum allowable voltage drop limits, and conductors must be sized accordingly to maintain voltage within these limits. Factors such as conductor length, material, and temperature affect voltage drop. Once the required amperage is determined, you can select the appropriate feeder and service conductors. Feeder conductors are the wires that run from the service entrance to the main distribution panel, while service conductors are the wires that run from the utility transformer to the service entrance. The size of these conductors must be sufficient to carry the required amperage without overheating or causing excessive voltage drop. The NEC provides tables that specify the allowable ampacity of various types of conductors based on their size, insulation type, and installation conditions. These tables take into account factors such as ambient temperature, conductor bundling, and the presence of thermal insulation. It is crucial to consult these tables and select conductors that are properly sized for the application. Overcurrent protection devices, such as circuit breakers or fuses, must also be selected to protect the conductors from overload and short-circuit conditions. These devices should be sized to trip at a current level that is below the ampacity of the conductors. The NEC specifies rules for selecting the appropriate overcurrent protection devices based on the conductor size and the type of load being served. In the example provided, a residence with a total connected load of 100 kilowatts is served by a 208Y/120 volts 3-phase 4-wire service. Using a demand factor of 0.35 from table 220.82, the total demand load is calculated to be 35 kilowatts. Dividing this value by the service voltage of 208 volts yields a required amperage of 168 amps. This means that the feeder and service conductors must be rated for at least 168 amps. To ensure compliance with the NEC and safe operation of the electrical system, it is essential to consult the relevant tables and sections of the code when selecting conductors and overcurrent protection devices. The specific requirements may vary depending on the jurisdiction and the type of installation. It is always advisable to consult with a qualified electrical engineer or licensed electrician to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. This will help to ensure the safety and reliability of the electrical system and protect the occupants of the residence from electrical hazard. Remember, accurately calculating the electrical load is essential for ensuring the safety and efficiency of any electrical installation. The general method, as outlined in the NEC, provides a comprehensive framework for determining the required capacity of the electrical system from the service entrance conductors to the individual branch circuits. By following these steps and consulting the relevant code sections, you can ensure that the electrical system is properly designed and installed to meet the needs of the residents. Consider that a panel board is the heart of the distribution system, and proper feeder sizing is critical to providing the proper voltage and amperage to prevent nuisance tripping and equipment malfunction. The panel board receives power from the main service entrance and distributes it to the various branch circuits throughout the building. It is important to select a panel board with sufficient capacity to handle the total demand load of the residence, as well as any future additions or upgrades. The power board should also be located in a readily accessible location and properly labeled to facilitate maintenance and troubleshooting. Grounding is another essential aspect of electrical system safety. The grounding system provides a low impedance path for fault current to return to the source, which helps to protect against electric shock and minimize the risk of fire. The NEC specifies detailed requirements for grounding systems, including the size and type of grounding conductors, the location of grounding electrodes, and the bonding of metal enclosures. A properly installed grounding system is essential for ensuring the safety of the electrical system and the occupants of the residence. Bonding refers to the practice of connecting all metal parts of the electrical system together to create a continuous electrical path. This includes metal conduits, enclosures, and equipment frames. Bonding helps to equalize the voltage potential between different metal parts, which reduces the risk of electric shock. The NEC specifies requirements for bonding conductors and the methods of making bonding connections. Surge protection is also an important consideration, especially in areas that are prone to lightning strikes or power surges. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage spikes that can damage or destroy sensitive electronic components. SPD are typically installed at the service entrance and the branch circuit panels to provide comprehensive surge protection. The NEC specifies requirements for the installation and selection of SPD. When working with electrical systems, it is always essential to follow safe work practices. This includes de-energizing circuits before working on them, using appropriate personal protective equipment, such as gloves and eye protection, and following lockout/tag-up procedures to prevent accidental re-energization of circuits. Electrical work should only be performed by qualified individuals who have the necessary training and experience. Regular maintenance and inspection of the electrical system are also important for ensuring its continued safety and reliability. This includes checking for loose connections, damaged wiring, and other potential hazards. Any problems that are identified should be promptly corrected to prevent further damage or safety risks. Staying up to date with the latest edition of the NEC is also crucial for ensuring compliance with current code requirements. The NEC is updated every 3 years to reflect changes in technology and industry best practices. It is important to be familiar with the latest edition of the code and to incorporate any new requirements into electrical system designs and installations. In addition to the general method and the optional method, there are other specialized load calculation methods that may be applicable in certain situations. For example, the NEC provides specific load calculation methods for dwelling units with electric heating or air conditioning, as well as for multi-family dwellings and commercial buildings. It is important to select the appropriate load calculation method based on the specific characteristics of the building and the type of electrical equipment being installed. Load calculations are not an exact science, and there is always some degree of uncertainty involved. However, by following the guidelines and methods outlined in the NEC, you can make a reasonable estimate of the electrical load and design an electrical system that is safe, reliable, and efficient. Remember that electrical codes and regulations are subject to change, so it is always important to consult with the local authority having jurisdiction to ensure compliance with the most current requirements. The authority having jurisdiction, or OJ, is the entity responsible for enforcing electrical codes and regulations in a particular area. The AHJ may be a local building department, a state electrical board, or another regulatory agency. Consulting with the AHJ early in the design process can help to avoid potential problems and ensure that the electrical system meets all applicable requirements. Ultimately, the goal of electrical system design is to provide a safe and reliable source of power for the occupants of the building. By following the guidelines and methods outlined in the NEC and working with qualified professionals, you can achieve this goal and create an electrical system that meets the needs of the building and its occupants. The NEC serves as a comprehensive guide for electrical installations, covering a wide range of topics from wiring methods to equipment grounding. Understanding the NEC is crucial for anyone involved in the design, installation, or inspection of electrical systems. The NEC is organized into chapters, articles, and sections, each addressing specific aspects of electrical installations. It is important to be familiar with the structure of the code and to be able to quickly locate the relevant information for a particular situation. The NEC also includes numerous tables and examples that provide guidance on how to apply the code requirements. These tables and examples can be extremely helpful in understanding the intent of the code and in making accurate load calculations. The NEC is not a static document, and it is constantly evolving to keep pace with changes in technology and industry best practices. Regular updates are issued to address new issues and to clarify existing requirements. It is important to stay up to date with the latest edition of the NEC and to be aware of any changes that may affect electrical installations. Continuous learning is essential for electrical professionals to stay current with the latest codes, standards, and technologies. There are many resources available for continuing education, including seminars, workshops, online courses, and industry publications. Investing in continuing education can help to improve your knowledge and skills and to stay competitive in the electrical industry. Collaboration with other professionals such as electrical engineers, architects, and contractors is also important for successful electrical system design and installation. By working together, these professionals can ensure that the electrical system is properly integrated into the building and that it meets the needs of the occupants. Communication is key to effective collaboration, and it is important to establish clear lines of communication and to share information openly and honestly. In conclusion, calculating feed and service loads for residences with three-phase services requires a thorough understanding of the NEC and the general method outlined in Article 220. By following the steps outlined in this video and consulting with qualified professionals, you can ensure that the electrical system is properly designed and installed to meet the needs of the residents and to provide a safe and reliable source of power. Always prioritize safety and adhere to all applicable codes and regulations. Remember, this information is for educational purposes only and should not be considered a substitute for professional advice. Consult with a qualified electrical engineer or licensed electrician for specific recommendations regarding your electrical system. The information provided in this video is based on the NEC as of a certain date and may be subject to change. It is always important to consult the latest edition of the NEC and to comply with all applicable local codes and regulations.